Okay. So this talk is about solving the diamond problem, and the main way to solve it is stop inherit data fields. And I designed a design pattern which I call DDIFI, stands for Decoupling Data Interface from Data Implementation. I think it's a clean and general solution to multiple inheritance. By clean, I mean I solved the diamond problem very cleanly, and I will show in this demo. By general, I mean this method, this design pattern, can be applied in a variety of a number of mainstream programming languages. I start with C++. It also can be used in Python, Java, C#, ISL, and D. And yes, it can be used in D, and I will show at the end of this presentation. And I want to stress, I mean, people know this interface implementation separation for a long time, but I want to stress it's data interface instead of method interface. So typically, when we, I mean, for example, talking about Java interface, we're talking about the method. We put method there. We have a method interface, and then you have the method implementation in the implementation class. But here, I want to stress the importance of data interface. So before I get real started, I have to disclose this work is patent pending. So I don't want to confuse anybody. Okay, next one. So I will talk a little bit about me, where I'm coming from, and my relationship with water and with D language. Okay. I got my PhD from Oxford University, and my thesis advisor is Professor Tony Hall. I think many of you should know his main contribution is programming language theory. That's got him the Turing Award. And I worked with him on process algebra. That basically CSP, if you know it. It stands for communicating sequential process, which is the Go programming language from Google based on. Actually, I should say, I did a PhD with him, but I'm not very interested in the parallel, in the concurrency theory stuff. Okay, I did a PhD. That's enough for me. I don't want to go any further in this direction. But in the same time, I'm also interested in OOP, that is the object-oriented programming. And I would say the language which influenced me most and Oxford is Eiffel. After I got my PhD, I come to States, and at a certain point, I joined Google. Google at that time using three main languages, that is C++, Java, and Python. C++ is mostly in the back end. Java is for the front end, and Python is kind of like a glue language. Okay, today Python is a king of AI, but at that time it's just a glue language. We use C++ very heavily in the back end. The whole back end depends on C++, but as everybody knows, C++ has lots of problems. So we have to constrain the programmer that what you can do in C++, you cannot do. There's a Google code, C++ Google coding standard to tell you what should do, what should not do. But at that same time, the company feel frustrated about the C++ and want to looking for alternatives. I have always, as I said, I have always been interested in programming languages. So, in one of the division that is kind of looking around. So I noticed the D from water for some years, for a long time actually. So I invited water to Google headquarters in California. At that time, I was based in California to give a talk about D. At that time, it's still pre 1.0 version. I think water must remember it. It's a very crowded meeting. Lots of people. I think more than, I don't know, 200 or 300 people come in, because at that time, Google itself is only like 2,000 people something. Okay, it's like 10% or 20% of the whole company come to Water's talk. After the talk, I checked with our EVP, Alan Eustace. We only have one exact VP at that time. That's Alan Eustace. I checked with him. I want to know what he think about D. And his impression is that, okay, it's a new language. It's try to be an improvement above C++ and Java, but we need it to be more mature and stable. At that stage, we cannot use D. This is something maybe I forgot if I told Water. But I have another story. Water, you still remember after the talk, there are lots of people talking with you, and there's one particular guy who talked to you for the longest time with European accent. You still remember him a little bit?
No, I remember you though.
Okay, you remember me, that's fine. Yeah, that guy and you are in the same room, a small room, and talked for the longest time after the talk. This guy, I tell you who he is. He's Robert Chris Mayer. He later, with Rob Pike and Ken Thompson, developed the Go programming language. Go. Yeah, that's him. Okay. He talked to you the longest time. I think at that time, he has something in his mind already. Okay. Sorry, where's my slides? Do I need to close this one? Sorry about this.
You probably went full screen, so you need to switch to a different. It's on a different desktop.
Let me just redo this.
Control down or command down on your Mac.
Can you see my screen now?
I can see the slides, but what I'm saying, yeah. I can
okay, you can, and you can see the slides. That's okay. Yeah. That's Robert, and I think the project actually started after the presentation of D, maybe 1 or 2 years later. Okay. The goal is based on CSP, but I'm not involved. As I said, I'm not interested in concurrency, and as a personal opinion, actually, I don't like Go. Personally, I don't like Go, especially the first version. It's too simple. For example, it don't have generic types, which is introduced, I think, only last year, 2022. They have generic types. You can have one single container for ins and floats. Okay. Anyways, that's Go. So, but Go actually emphasized another aspect of Google engineering, that is concurrency, because we need to in the infrastructure we need to handle so many machines, so many requests, which the approach is quite different from the conventional language like C++, like D. Okay, I think that's the other reason that that Google want to develop its own language and eventually release at Go. Okay, that's my Google story. After that, I'm doing my own startup, and as many people who do startup, you want better programming, developing tools and programming languages because you want to be more efficient than the big companies. So I always looking for better languages, and over these years, I mean, there are many newcomers. Okay, that's a brief introduction about myself. Now we're talking about the main topic of this presentation. It's multiple inheritance. I will give a little bit overview. So, multiple inheritance has been around for a long time. I mean, academically. C++ is definitely not the first one to have multiple inheritance, but it's in the mainstream. I mean, in the popular language used in the industry, it definitely is the number one OOP language which support multiple inheritance. When people in industry in the company start to use C++, well, we found lots of headaches. Okay, I'm only talking about multiple inheritance. I mean, there's other problems. We don't talk about it in this presentation. So most notably is the diamond problems. Okay, you have this name clash that you cannot resolve easily. So the later languages like Java, C#, including D, start to abandon multiple inheritance because they think, okay, this is too much trouble, both for the compiler writer and for the developer. Let's just get rid of this feature. That's fine. So they use single inheritance plus multiple interfaces. And in the interface, you only have a method or prototype instead of the implementing code. But however, if you really, I mean, doing engineering work, you will find that sometimes you do want to reuse the implementation code. The single inheritance plus multiple interfaces is not enough. Okay, so people start to try other approaches, try to add back some kind of functionality of the multiple inheritance. For example, trend in Scala, PHP, and mix in Ruby, Dart, and including D. Okay, that's, I think, two problems with this trend and mix-in approach. The first one actually is some form of multiple inheritance crept in already. For example, I mean, this is a D community, D talk. I mean, give a D conference talk. Okay, so in D, you can do multiple inheritance plus multiple templates. Okay, and sometimes you can even do a alias this. Well, that actually is a multiple inheritance. Okay, not in an official way, but it creeps in. So that's the first problem. The second problem is, well, it have the same problem as the original multiple inheritance problem. That is no clean solution for the name clash, especially for the data fields. I myself, I'm doing this startup, so I use a number of languages. So I myself sometimes, okay, always want, I don't want to write a duplicate code. Okay, I want to reuse my implementation code in some way. Okay, so I tried lots of different approaches. It never succeeded. And I always want a clean solution for multiple inheritance. eventually, at the beginning of this year, I came up with design pattern, which I call DDIFI, which will cleanly and generally solve this problem, which I will show. So let's go into the detail. What exactly the problem is. So we start with the diamond problem. That's our motivation. So we start our code from the Wikipedia about this problem. So the diamond problem is ambiguity that arises when two classes B and C inherit from A, and the class D inherits from both B and C. If there's a method in A that B and C override, but D does not override it, then which version of the method D does inherit? Is that B or is that C? Okay, actually, based on this description, first thing I want to say is it's application semantics. Okay, you want to use the version, that method version from B or from C, is application semantics. There's no compiler rule can help the programmer to choose it automatically. Okay, it has to be explicitly specified by the programmer. Okay, so also based on this description, actually it's very easy. The solution is in the problem description itself. It said D does not override it. So why do you have such restriction? Just the programmer can just override it. That's very easy. Okay, and then is that from B or is that from C or even from A? Okay, you can use the fully quantified name. Then the problem solved. Okay, so the real problem is not, in this diamond problem, it's not about method resolution. The more difficult problem is in the fields resolution, because the fields will cause us more problems. Okay, let's continue with more concrete example. So this is the example. Suppose we model people in a university. At the top of the hierarchy, at the root, you have this person. Okay, and in this diagram, all the class layout is flattened. So for each person, you have a name and you have an address. Then you have student inherit from a person, and the student have the name, have an address. That's fine. On the right-hand side, you have faculty. A faculty also have a name, have an address. That's fine. It also inherits from person. Pretty good. But I want to point out here, the name is still the same. Each person can only have a single name, only one name. That's fine. But the address at this point actually have two different semantic meanings. In student, it uses it as a DOM semantics. So if you have a regular method, some functionality, some application method, the student want to take a rest, you take rest in DOM. So the semantics of the address in the student class is DOM. And for the faculty, it uses the address, it assigns the semantics of the address as lab. When the faculty do some bench work, he do it in the lab. So the address, that field, right now at this level have two different semantics, but we still use the same name, same field name called address. That actually is the root of the problem. Okay, let's continue with the bottom class, the research student. The research student inherit from both student and the faculty. As an idea semantics, okay, it should have only one name field, but two different address field. One as student is student address to take rest, and the other address is faculty address to do bench work. So ideally, in research student, it should have only exactly three fields. So it need to achieve the field name got joined, but the address got separated. Okay, that's ideal semantics. But with C++, its native, its plain multiple inheritance mechanism, this is not possible. And okay, this slide basically just summarize what I just described on that diagram. So the separation is, we wanted the name to be joined, but the address to be separated. And separation actually is easy. You can use fully quantified name, like student address or faculty address. But how to join the fields, that is student name, faculty name, into research assistant name into one field? Okay, that's the main problem we want to solve. In my method, actually, my design pattern is mostly designed to solve this problem. So we will only discuss fields, how to solve this fields problem. And we start with C++ plain multiple inheritance mechanism. That is virtual. Two virtual and not virtual. I intentionally introduce a macro which define virtual to be either virtual the keywords or it's empty. And this is a very simple class definition. You have person and you have student inherit from person. You have faculty inherit from person. You have a research student from inherit from student or faculty. And you put the macro definition of virtual there. If you define virtual and the keyword virtual, okay, you end up in the research student have one name and one address, only two fields, both get joined. If you define virtual as empty, then you got two names and two address. You got four fields, okay, both got separated. So it cannot achieve the idea application semantics we're talking about. We want exactly three fields with one name and two address. So next, I was trying to do some research, try to understand, try to figure out a way to do this. So the first thing I'm doing is to study the C++ multiple inheritance memory model, how the memory layouts. Okay, and I search on the web. I study all kinds of material. Here I show three of them. I can assure you, this talk is not about the memory layout. I'm showing these three diagrams only to show how complex, how difficult it is. Okay, so the first diagram on the top left, actually is the one matches the diamond problem we just described. So it basically draws the top, that's the top class, the left class, the right class, the bottom class, and also with its corresponding virtual tables. At the diagram on the right, it's some kind of inheritance hierarchy. What I want to show here is the two different kind of errors. The dashed error is virtual inheritance. The regular solid error is non-virtual regular inheritance. So it's even more complicated because you have different combinations of this virtual inheritance and non-virtual inheritance. Okay. if you consider these combinations of virtual and non-virtual, the memory model, the memory layout can only be even more complex. At the bottom left, this small diagram is what I found in a patent from Microsoft. It also shows some way to dealing with multiple inheritance. It's very small. Basically, it inherits from A, B, C. Basically, it's multiple inheritance, and it shows how to do this in a kind of tree kind of structure. Okay, so after I studied all this material, I realized it's messy. It's messy. Okay, so again, come back to our original application question. You have this inheritance hierarchy. You want some of the fields inherited from the base class be shared and others be separated. And on the actual machine, we have a linear space. How would you align these different fields into this linear memory space to achieve this goal? And also, how do you handle, what's the proper rule, of the proper compiler rule to handle all the combination of these different scenarios? Okay, that's difficult. We can, at this point, we kind of understand Java, our D, our C# rationale that why they choose single inheritance instead of, totally abandon multiple inheritance. In single inheritance, so from the very bottom, you look at my top graph, the graph in green color. Suppose the node 1 is the bottom of your inheritance tree. Okay, its path to the root is a single path. It's a single path. Then you can single path, which means it's linear. Okay, you can easily tell the different fields from the classes. Just tell them according to this inheritance sequence. You are done. It aligns perfectly with the linear space, memory space. Then let's look at the multiple inheritance. Let's look at the multiple inheritance. That's my bottom diagram. In the multiple inheritance, the hierarchy actually form a lattice. Okay, it's a lattice. Then the problem is the memory space is linear, and you have different rules. Remember our goal is some fields got joined, some fields got separated. So the problem is, how would you lay out such a lattice in a linear space? Okay, that's my very kind of informal way of thinking. But I think okay, this actually at least explains to me why the C++ memory layout is messy. To me, it's as clear as mud. I don't think there's an easy rule to handle it. Both, from a compiler implementer's perspective or from a developer's perspective to understand it. Okay, so I think, okay, this is too messy. Maybe we should just get rid of it. So that's how I designed my pattern. If we get rid of all the inherent fields, then what should we use? Okay, here on this diagram, I have this person class. Okay, it need to implement all these regular methods. When you implement a method, some functionality, some application methods, you need to use some fields from the class. Okay, what do you do? Okay, we have accessor method. It suddenly comes to me that we can just define abstract property method to be used in these regular methods. Then you can write your regular method the same way, with the only exception that you use the abstract property method instead of the direct raw fields directly access it. Okay, then we can introduce the actual implementation class. That is the lower part in my diagram. That's the person implementation. In this implementation class, what I call data implementation, you actually define the actual fields and you override the accessor, the virtual accessor property function to return the raw field you just defined. At this point, if we go back to the person, that is the upper part for my class definition, we will say all these regular methods can be code reused. You can inherit from person, but not from a person implementation. You inherit from person, and all these regular methods can be reused. And the most important thing is all the property methods are virtual. You can override them. When you override them in the derived class, you can achieve the application semantics that you wanted in the derived class. So that is, you delay your data definition only to the last point in the implementation class, what I call data implementation. Now we compare, how we got here. Okay, so initially we have this procedural programming. You define struct as a bunch of fields definition. And then you define a global, at the global level, a function which use this struct and access its different fields. Then we have this OOP, object-oriented programming, which bundles the data and the method which operate on this data into one single unit, which we call class. That's how the object-oriented programming coming from, which works pretty good, actually. The only problem we are facing now is multiple inheritance, which currently cannot be handled nicely with plain OOP. So I come up with this DDIFI design pattern, which we do it in this way. The top class is still different mapped from the regular OOP programming. The only exception is instead of define your raw fields in this class, you define virtual property method. And then you introduce another implementation class, which actually defines the raw fields and provide the property methods. In this way, I will show we will solve the multiple inheritance and the diamond problem nicely. It's time to work through the code. Before we dive into the code, I want to once again stress the importance of I showed earlier, that is semantic branching. That's a concept I showed in this this diagram. Okay, the address at student and faculty level actually assigned different semantics to the field, to the address field. We call person as the branching point, as the semantic branching point of a field address. That's one very important concept we will use to make our explanation easier. Okay. Continue. And for field drawn, as I have just showed here, right now, after my separation between data interface class and the data implementation class, we are only dealing with the word true property method right now. So for the field drawn operation, it can be achieved just overriding the word true property method of the same name. For field separation, which will be achieved by define new semantic assigning properties. Okay, it's time to go. The first class is the top class we define. That is class person. And we define, instead of define raw fields, we define two word true property methods. And in the person implementation class, we actually define the raw fields and provide the property word true methods implementation. And all the public or protected record methods are defined in the data interface, which will be inherited and code reused. In our example, for this person, it's too simple, so we don't define anything. But if you do, you will define here. Now we're talking about the faculty class. The faculty class will inherit from the person class. Now it's as we said, person is the semantic branching site of the field address. And in faculty, we know the faculty will use, will assign the address to give a semantic meaning as lab. So you name it explicitly. You define a new semantic assigning word true property, which is called a lab. And in this, we are only develop this faculty class right now. So we don't want any other new fields to be introduced. So inside this lab word true property, you can just return the address, which is from the superclass, the address method. Here is an example. How would you write the regular methods? You can implement your regular method right here in this do bench work. So in this do bench work, you will use the lab, the newly introduced lab method. It must be, it must use this lab new property instead of the address, because the address field, as we know in the inheritance hierarchy, it has branching semantics. If you use address here, you will have semantic trouble when you assemble your whole system, different class together. And also, from a program or code reuse point of view, if you read this do bench work implementation, you will read do bench work in the lab versus do bench work in the address. Certainly, the first one sounds more naturally, so it's more correct to do. The faculty implementation class basically implement the data implementation, provide the data implementation of the faculty class, it's not required to inherit from any of its superclasses data implementation, but it's still an option. If it fits, you can still do it. Okay, so let's go back to its parent class implementation. It has name, it has address. Okay, I can just reuse it. Then I can let faculty implementation inherit from person implementation. That's fine. We can just reuse the code. Okay, we come to the student class, which is the same rationale I just explained in the faculty class. It's the same. We introduce a new semantic assigning virtual property, which is called DOM. And in the regular method, take rest, we will use this DOM property instead of the address property. And for the student implementation, it's the same. We can, firstly, it's provide data implementation class to student. And we can also reuse the person implementation class, the data members here, the actual data members name and address here. Okay, so it's also code reused. So in this way, it's both memory-wise efficient and functionality-wise flexible. Now comes to the bottom, the final bit of the diamond. That's a research assistant. Firstly, the research assistant data interface class just inherited from student and then from faculty. That's all. And because of multiple inheritance, all these regular methods do bench work from faculty and take rest from student are inherited. The implementation are inherited by the research student. You don't have to do anything. Now we come to the data implementation class of research assistant. It just inherits from its data interface, nothing else. I mean, for comparison, you can say student implementation still, I mean, for the convenience, inherit from person implementation, and faculty implementation also inherited from person implementation. That's for convenience, for code reuse. Here we cannot code reuse it because we want to solve the diamond problem. We want to give exactly 3 fields to research assistant. And you can do it here. You define one single name. You define 2 different addresses. That's faculty address, that is student address. And these 3 fields are totally independent to the fields in person implementation. In person implementation, student implementation, and faculty implementation. Okay. After you define the, I think it's the wrong side. Okay. Yeah, this one's right. Yeah. And after you define the 3 different fields, you also override the virtual property methods, basically to return the corresponding raw fields you just defined. And here you can also assign different, semantics. For example, in this research assistant implementation, I want the DOM to be its main address. You can do it. That's the second virtual property. So I return DOM as the address. For name, I return name. For DOM, I return student address, the raw fields. And for lab, I return the faculty address as the raw fields. Okay, here we can see clearly that we only have 3 fields actually defined. Now let's write the application, the functionality code. Okay, we make a factory method which returns the research assistant implementation. and we create such an object. We call its two methods on it: do bench work or take rest, and we also assign this to it, this object to its parent pointer, the type, and call the same method. We can say clearly that the name is joined, one single name and the two different addresses separated, and achieved the ideal semantics that we have wanted initially. And when we program in this way, we can also do an alternative implementation. This is just another example. Suppose for biology research student, okay, I mean, maybe it will work in two different labs, lab A and lab B. It alternates between two labs because you want to give the microorganism some time to develop. Okay, so it's just an example. Suppose you do A on Tuesday and Thursday, and you do lab B. You're in lab B on Monday, Wednesday, and Friday. Okay, then we can implement the lab property methods as a function instead of raw fields. So in this bio research student implementation, you can only define two different fields, that is name and the student address. For the lab semantics, here you can choose to define it as a function. You look at what weekday this is, and then you decide you go to lab A or you go to lab B. Okay, so this example again, I want to illustrate that this research student implementation is totally independent to those fields in person implementation, student implementation, and faculty implementation. That's the key why our design pattern succeeded here. The rest of a few slides is we basically try to formalize these new programming rules. Okay, so the first rule basically says that to model an object for, you need to split data interface class and the data implementation class. In the data interface, don't define any actual fields because it's intended to be inherited multiply by the derived class. For the full implementation class, it provides the data implementation, and it actually contains actual fields and implement the property methods. The rule 2 specify what you do in the data interface class, that is the word define virtual property and implement. This is very important. Implement the public and the protected regular methods in your data interface class because they will be multiply inherited, which means all these regular methods implemented the code will be reused to achieve, the main goal of multiple inheritance. And also, you should add a static factory method to create the actual objects. The rule 3 tells what we do in the data implementation class. In the implementation class, you can actually introduce the actual data fields. And you also have the option to do it while computation. It's either do it in memory, physical memory location, or you do it through computation, as we showed there in bio research student, lab A or lab B. Then you can also implement the private regular methods, which all depends if you want that part of the code to be reused. If you do it here, you can use the raw fields directly instead of calling the virtual property method, which is a virtual function call anyway. Here you can directly use it. But if you really want this to be code reused, okay, then firstly it's not a private regular method. You probably want to change it to protected method, and you move that implementation into the data interface class. Rule number 4 is about subclassing. So subclassing, suppose a bar inherit from 4, then make a bar inherit from 4, and override the virtual property method according to the application semantics. You can even need to introduce the new semantic assigning properties. As the data implementation class of bar, that is bar implementation, it need to inherit from bar itself. Of course, it need to implement it. But its own implementation is independent from the full implementation. It's still an option to do it, as we have showed earlier in case of faculty implementation inherited from person implementation. It's still an option to do it if it's right, if it's convenient. You can still reuse that part of code. But it's not required to do so, because when there's conflict, you need to define your own fields. That is the case we have showed in the research assistant implementation. So we want to stress, this is very important, that there's no data dependency of bar implementation on full implementation. Okay, rule number 5, add and use the new semantic assigning property after semantic branching, which we have talked earlier. That if you have a class C which is the semantic branching site of a property P, then in every data interface class D that immediately below C, add a new semantic assigning property B prime. And it's a different name. And then in all the regular methods of D, use this new property P prime instead of the P, the original P, because its semantics has branched. You cannot use it anymore, according to the corresponding application semantics. This is how we handled the fields, the property person, the address. That's basically, how to formalize into programming rules. So in summary, the goal is to make the field drawing and separation as flexible as possible, and to allow programmer to achieve his intended application semantics. And it can be achieved by either drawing, which is overriding the corresponding virtual methods of the same name in the multiple base classes, or field separation be achieved by implementing or overriding the new semantic property that we show in Rule 5. After I have done this, okay, I realized it depends on the regular methods implementation without the concrete field definition. if you read this sentence again, does it remind you something? Okay. Oh, it's not showing in my. Oh, it's empty slides. Okay. Yeah. That is the default interface method which Java introduced in 2014 and C# introduced in 2019, and it's kind of funny because firstly, when both these languages first appeared, C# is 5 years later than Java, and for this default method, it's also 5 years later than Java, and they also carry the same version number. Anyway, it's a funny thing I found out, and this is exactly what is required. The new design pattern DDIFI required, which means we can have clean multiple inheritance in both Java and C#. And I will briefly show it. This directory contains the DDIFI implementation in Java, C# and Python. Here we only look at the Java. Okay. The Java is easy. For person, you define a virtual property, that is name and address. That's all. There's no regular methods for this simple class. We're done with it. In the class person implementation, we actually define the actual fields, and then we override. We provide the virtual property method implementation. In the interface faculty, it inherits from person, and it introduces the new semantic assigning property after the semantic branching, that is lab. And then we implement this regular method, do bench work. And in this do bench work, we call this new property method, new semantic assigning property method we just introduced, that is lab. And this code will be reused. In the faculty implementation, it's same again. It first need to implement the faculty data interface. And here we can also code reuse person implementation, which is we pull in the concrete field, name and address here, and it's code reused. In student, we do the same. You introduce new semantic property that is DOM. And in the regular methods, you call this DOM instead of the old one, the address, which has been semantic branched. And in the student implementation class, again, it need to implement student interface class itself, and you can pull in, which is the code reuse, the person implementation, and you are done. You don't have to do anything. And for the research student, it inherits both student and the faculty, and then you pull in, you basically code reuse all the regular methods, that is take rest and do bench work. And here you provide a factory method, that's it, very easy. And in research assistant implementation class, you actually define the 3 different fields, the concrete fields, and you provide the virtual property, you override the virtual property. And we develop the application, same application, sample example application before, and call the methods on it, and you will find out it achieved what we want. Single name, 2 different address. So that is Java, and for C# is basically equivalent, and Python almost the same as C++ because Python also have multiple inheritance, and we can also. Oh, I have to reload this. Yeah, so we showed our demo in Java. So at this point, I think both Oracle and Microsoft can rebrand their Java and C# as the clean multiple inheritance language. I mean, maybe they still didn't realize it. And if we look back in retrospect, the C++ from its version 2.0, that is the first time it introduced the multiple inheritance into the language, actually it has the language mechanism that can achieve what we used, what we designed, this DDIFI pattern to achieve clean multiple inheritance. But for decades, people avoid multiple inheritance mainly because of the diamond problem complexity. But we solved it today. The DDIFI implementation, this design pattern in other languages, if you are interested, you can do it yourself and compare with my sample code there. And since this code is, this meeting is in D community, I will also show it how we do it in D, clean multiple inheritance. We can do it right now with the current compiler. So person, you define name and address, the virtual property. And the implementation, you use the concrete field and define the concrete field and redefine, provide the virtual property methods. For faculty, there's a little bit complexity here. Firstly, as the data interface, we do the same. We introduce a new semantic assigning property that is lab. And because currently in D, you cannot have default interface methods. You only have methods prototype here. So we basically only define the do benchwork prototype here. To be able to simulate or implement this DDIFI pattern, design pattern, we can do it as template mix-in. You define a mix-in template, and this mix-in template has a parameter, which is do you want to, with or without overriding the virtual property. For the faculty implementation itself, is definitely want to override. So here you pass true with override property, and then we'll basically provide the overrided lab implementation. And here in this mix-in template, you implement the do benchwork regular methods. Then the faculty implementation just mix in this template. Okay, for student, which is in symmetry, we do the similar thing. Its definition, data interface definition is straightforward, and its template mix in, it's similar that you have with virtual override property parameter, and in the student implementation you pass true, you actually override it, that is DOM, and you in this mixed-in template you provide the method implementation using this new property, virtual property you introduce, that is DOM, and you can do it here. That's fine. Then we can reuse the two template mix-in we just defined in this research assistant. The data interface class is simple. It's just inherited from student and faculty, and it provides a factory method. And in the implementation, data implementation class, you define the actual three fields, and you do the mix-in. This time, you pass false. You pass false into the parameter, the template parameter, because we want to override those new virtual property right here in this research assistant implementation using the newly defined fields, raw fields here. Okay, so then you define this virtual property methods to use your raw fields. And these two template mix-in will pull in, basically means code reuse your implementation code. That is take rest and do bench work. Then we're done. That's the same application code, and it will generate the same output. And we achieved clean multiple inheritance in D.
Can you jump back to in your code there?
Okay. Wait. I will go back. The D code, right?
Yeah, the D code. Yeah.
Okay. Wait. Okay.
The part that says I didn't.
Which line? You can tell me which line.
I just wanted to see because you had the Boolean.
You can check it yourself on the GitHub actually.
Yeah, no, I could look at it, but right now I'm recording the screen.
Okay,
so
no problem. No problem. Take your time.
No, I just was wondering on the Boolean that you pass in.
Oh, the Boolean pass in. Okay, it's a static if. Yeah. This one is a static if. It's a static if, which means the compiler do it and the compile time. It either compiles in this function or will not compile in this function.
Okay. Right.
Yeah, it's a static if.
Yeah, no, I just didn't. I couldn't see it because after you introduced it, I didn't understand. I didn't remember what it was for.
Okay. It basically if it's student implementation, you need to pass in true, because you need that implementation. But in the research assistant implementation, you don't want that version. You want to define your own version.
Yeah.
Actually, yeah.
What I was concerned about, what I didn't understand is what happens. Like, what is the other stuff that's included? Because it seems like that's the only thing that you were.
What's the other stuff? That's the other stuff. It's the regular methods that we want to code reuse.
Yeah. Okay.
Yeah, that's the benefits of multiple inheritance. That's exactly why we want multiple inheritance. We want to reuse the implementation code of the regular methods.
Okay, great. Yeah, that's just what I wanted to understand. What are the things that are included if you had it as false?
Right. So, which basically this take rest regular methods implementation is both available in student implementation and research assistant implementation. That same piece code is reused, which is not possible in single inheritance. But here we did it.
Yep.
Yeah, we did it. So that's the reason. I mean, you interrupted me. Actually, it shows my point. I think that's my thought is. I think it's a little bit convoluted. It's a little bit hackish, And that's the reason, actually, I told Walter, I want him to be in this presentation. I want D to introduce default interface methods as Java and C#. Then we will have the clean multiple inheritance just I have showed in Java. So right now you can do it with template, mix in, and static if in the current D. But it's a little bit hackish. Okay, if we have default interface methods as in Java and C#, it's much cleaner to achieve multiple inheritance, clean multiple inheritance. Then we can brand D programming language is a clean multiple inheritance language. Okay, that's the other goal. That why I want to come here to do this demonstration, and I particularly want Walter to be in this demonstration to hear me. Okay. Next, we compare what are the pros, the cons. For,
Dan, I think you're just going to have to talk in order to...
yeah, sure. We'll have a question and answer section after my talk. Okay.
I do hear you, Yushin.
Okay. And I'm almost finished. Only 2 or 3 slides. Okay. So pros and cons. Pros is clean, as I have showed you. It achieves field drawing and field separation cleanly, exactly as to the application semantics. General, and I have showed it works in the current mainstream sets, the raw fields, instead of calling virtual functions, virtual property methods. And also, there's another way, even in public or protected method. You can always use local temporary variables. Okay, you first read through the virtual property to store that fields that you want to read, and then you do your computation. After you do your computation, you write it back again through the virtual property methods. In this way, you reduce the virtual function cost to read and write. Maybe once or twice. I think that's pretty efficient. So I think this is not quite a very big concern. Okay, I'm almost done. So the general guideline to the developer, and I think also to the compiler writer, is this. For the planned, that's firstly, if the language if you choose do have native multiple inheritance mechanism, and your multiple inheritance hierarchy in your application domain is planned, and you're absolutely sure that there's no name clash, it's name clash free, then use the language's own multiple inheritance mechanism. Otherwise, for unplanned multiple inheritance, for unanticipated field name clash, you use my pattern, that is design pattern, that is DDIFI. You define the field as a virtual property, and you write your regular methods using this virtual property, and you can even choose to implement this virtual properties by either the actual data fields or through computation. Finally, this is my last 2 slides. Finally, as an analogy, I will describe it in this way. The fields are like the legs of the table. And on top of these legs, we build application functionalities, that is the methods, computation. And for example, you want to place apported plants on top of a table. And but in some scenarios, in this case, that is multiple inheritance, this solid legs is causing us too much trouble. Okay, we cannot do property a proper code reuse, okay, and we don't want this solid legs, then you can do this. That is virtual legs, which is more flexible. Now, that's my end of my talk. And I'm happy to take any questions you may have. And I will keep this video on. I'm done.
How about making a specific proposal for what you want with defaults and abstract classes?
You want a design doc or what?
What?
I mean, you want a design document or what? What do you want?
Yeah, just a page on your idea on defaults for abstract functions.
Right. Okay.
What it would look like. Yeah, I appreciate that.
Okay. What it look like? Okay, that's fine. But on top of my mind, I will just simulate what Java and C# is doing right now.
All right. Well, I don't know what they're doing right now.
Okay, that's fine. That's fine. No problem. I mean, I know you have written a Java compiler a long time before. Maybe, I know this Java default method is introduced in 2014, but maybe you didn't follow it. That's fine.
I implemented Java back in 26 years ago, and
I see. Okay.
I have not kept up with improvements to it.
Right. Okay, no problem.
Yeah, there was a question in the chat here from Ricky, I think.
Okay, I didn't. How to see the chat? Okay. Because I'm doing implementation, I didn't.
Right.
Sorry, what's the question?
It said, "Have you studied ML signatures?"
No. The main reason is I'm more on this. I mean, when I choose languages, I'm more on this C++, this Java camp. I'm more following this direction. ML, I used that before, but I'm mostly doing functional programming. I know it can do OOP, but I didn't follow it. It's kind of like what happened with Walter on Java. I mean, he did a Java compiler like 26 years ago, and I was using ML maybe 20 years ago something. I didn't follow their approach, especially when I use ML at that time, I'm mainly use it for functional programming. I didn't use its OOP part of it. Any other questions?
No, I think there was some elaboration there in the chat by Ricky. I didn't follow it completely, but I think there was a link there. Also.
I think.
I can send the link. I can send the link, the repo. So if you want look at it yourself, that's fine.
Yeah, I think that regardless of the applicability of this for your design pattern, having default implementations for interfaces that just use the known interface functions is still a nice thing to have in general, because sometimes you just want that. You even with single inheritance, you don't need it for multiple inheritance.
Yeah, that's right. I think people want multiple inheritance to reuse the implementation code. I mean, if it's just a method prototype, it's too limited, and it may lead to code duplication. Okay, I saw there's a comment that classes are entirely wrong, wrong way to do OOP. Okay, I have no problem with that. I mean, there are many opinions regarding OOP, but I mean, previously, I'm doing some academic work, and I also doing this engineering work. Doing this engineering work, you have to face the reality. I know something. Well, we have opinions, but we also need to look at what's available on the market. Especially, there are two aspects of it. Firstly, is the language. Okay, what the language provide, how mature the tooling is. Okay, there's the other aspect that is human resource. Are you able to find good programmers in the language that you choose? Okay, so sometimes you go with mainstream. You have to, because otherwise you it's very hard. Suppose let's just suppose I'm just taking one example. You choose ML or whatever. Are you able to find capable programmers, developers? It will be hard, especially for startups. Oh yes. How do I stop it?
I think you just, yeah.
Oh, stop. Yeah, okay, I saw it. Yeah, I'm done.
Yeah, it was a great talk. Thank you very much. I think in general, having default interface methods would be a really good addition to D, and if it opens the possibility of saying, well, you can now do multiple inheritance, I think that's a really nice additional benefit to that feature.
I agree. It's a good idea.
Now, what are you what are you planning on charging for the patent?
Oh, okay. I have a little bit of thought on this. Firstly, don't worry about it, because I'm doing a startup myself. If your company have less than 1 million revenue, it's completely free. Maybe you just mention it in the doc or in the code that you use this pattern. If it's over 1 million in annual revenue, probably I will charge like I don't know, for every 1 million revenue, maybe $10. $10, I can get a coffee.
That's pretty reasonable.
Yeah, that's how I want.